Okay. So the plan for today is to talk about limits. So that's the last topic for the exam. Just remember that the exam, so it's going to be next Wednesday during class. So I'll give you extra office hours next week. I'll send you an announcement about that. And I'll say a couple more things about the exam, after I have finished talking about limits, just in case someone else, shows up. But yeah, so today we'll done with the material. So just as always, let's start like by recalling a little bit about how limits work in Calc 1. Um, okay, so in Calc 1, um, you know, there are like the interesting limits in Calc 1 are those which look like 0/0. That's one way to think about them, right? So for example, if you had something like this, like x² minus 1 over x minus 1, right? Well, the idea is that you cannot quite plug in x equals 1 directly, right? Because if you just try to plug in x equals 1, you get 0 here and 0 here, right? So that on its own is undefined. And then, yeah, since you already know L'Hopital's rule, then like you could just say, well, let's just use L'Hopital, which is true, but like, there was like a more like elementary way to find this limit, which is just do some factorization, right? So you would do something like this. And then like by doing that, like the x minus 1 cancels, and you just get this limit. And the idea is that now the expression is 1 where you can actually understand what happens as x approaches 1, right? And then you just get 2. So there are like types of limits in calculus where like you just have to play a little bit with algebraic expressions, right? Before like finding what the actual value for the limit is. Um, and then, so that was one way to find, whether a limit exists or not. Another type of limit that you would have seen is, for example, something like this. Um, hopefully this looks familiar. Like you have the limit as x goes to 0 of absolute value of x over x. So what happened in this case is that secretly, if you think about absolute value of x, well, what's the absolute value of a number? That's x if x is greater or equal to 0, or negative x if x is negative, right? So essentially, like by using absolute value, you are kind of like defining the function, like a function piecewise. So the best way to like approach that type of limit was by studying the one-sided limits. So and this will be actually important in what I'll say in a second. So to study this limit, you would do like, the one-sided limit as x approaches 0, using positive numbers, right? But the idea is that once you are approaching 0 with positive numbers, then the absolute value of x can be replaced with just x. So you get x over x, and that's just 1. So the x's cancel, and you just get 1. And the other one, if you use the other one-sided limit, you would get negative x on the top, and then the x's cancel again, and then you just get negative 1. Right, so if you want, here's like, here's one way to think about it. Like if you take the real line, the number line, then there's a value 0 here, right? And so for the first limit, you're kind of approaching. For the first one-sided limit, you're approaching zero using positive numbers. And here you're finding that the limit happens to be one. And for the second other one-sided limit, you're approaching it, the origin using negative numbers. And here you find that the limit is -1. Okay, so the overall conclusion was that this limit could not exist, right? Because the two one-sided limits were different. So here, the idea is that then the limit itself, right, as x approaches 0, does not exist. Hence, one-sided limits are different. Is that okay? Is that good? Okay, so here's like the first difference. Now with this preamble, I can start telling you like the first difference, the big difference between what you did before and what you're going to, the types of limits that appear here. The good thing about limits is that, good and bad thing is like it really like we don't use them anywhere else, but it's just to understand a little bit of what's happening, what the idea behind them is. So let me just give you an example. Like, let's say you wanted to study. Okay. So now we're trying to understand something like this. Like this is like the version in two variables of what a limit would look like. So you want to study something, the limit as x, y approaches 0, 0 of like a function, like for an expression that depends on x and y. Okay, so what does that mean? So what does this mean? So what this is asking is, how does, what this is asking is how does the expression, right? Behave as the point, right? Oh, let me see if I can move this a little bit. So what you're asking is how does this quantity behave as the point x comma y approaches the origin? Okay. So you have to imagine that you have like x, y somewhere in here, but you can put it in any quadrant, but just to and here you have 0, 0, right? So you can evaluate this expression at different values of x and y, right? And then you are asking how the numbers that you get behave as the thing, like, as you start moving the point closer and closer to the origin, right? Now, the main difference, between this situation and that situation is that when the limit, like, for example, was as x approaches 0, there are only two ways to approach 0, right? You could approach 0 from using positive numbers, right? Like from the positive x-axis, or using negative numbers, right? From the negative x-axis. So in a sense, there are only two one-sided limits, if that makes sense. Like, when like you have like the regular Calc 1 limits. Now, the analog of the question, like for example, is like how many ways are there to approach the origin, right? If you take like a random point on the plane. So for example, if you start with a point on the first quadrant, one way to approach the origin would be like to use like kind of like a straight line that connects these 2 points, right? That would be like a way to approach it. But another way could be kind of to try to move to the origin, like using a parabola. That would be another way to approach the origin. Another way would be kind of a lot more crazy, like you just take like some random curve that goes to the goes through the origin. So what I'm trying to say is that you know, before, like, to connect a point to the origin, there's really only two ways to do it, depending, like, or one way, like, depending on whether the point is to the left or to the right of zero, for example. But here now, once you, there's so much more room. That's what's happening now. So because there's a lot more room, like an extra dimension, you know, there are tons of different one-sided limits, if that makes sense. So the whatever this limit is going to be, the condition for the limit to exist is that it must give you the same value for any possible path or trajectory that gets to the origin, if that makes sense. So let me write that down. So the main difference is that now there are infinitely many one-sided limits, if you want to think about it in that way. So now there are infinitely and for the limit to exist, the answer, the limit that you get must not depend on the particular way you took to reach the origin. So for the limit to exist, the value that you get cannot depend on how you reach that point. So I'm about to show you what I mean with this particular example, but is that making sense? Like the important thing for now is that the difference, like before, is that you can only come from, like, you know, from the right or the left, and now you can come like at all different angles or possible directions. So, you know, like spiral down to the origin or moving through straight lines, parabolas, like a bunch of different like possibilities. So the fact that there's more room on the XY plane means that there are like more variations of how you could take the limit. So let's just work this out a little bit more concretely. Just to illustrate this, again, you want to understand this expression as you get approach to the origin. So the idea is that you can choose a path that passes through the origin. So or a curve, if you want to think about it as a curve as well. So what is a curve that goes through the origin? For example, a straight line, right? That's something that goes through the origin. So what is an easy straight line? I mean, there are tons of options, but let's just start with something simple, and then I'll give you like a more general method that works. So you could just move like along the line y equals x, right? So just imagine that you have like the line y equals x, and you're going to start. It actually doesn't matter where you started, but like, I mean, you could have started on either side of the line. That's fine. But what I'm trying to draw here is that you have to imagine, since it's the limit, that you're walking towards the origin, right? Because that's where you want to study the limit. So you want to understand the behavior of this quantity, right? As you approach the origin, okay? Now, the reason why I do it this way is that once you choose a specific path, right? Like, if you see it here, like, this expression depends on two variables, x and y. But once I fix my favorite path, then, like, there's like a relation between the variables. So actually I can turn the limit into a limit of a single variable. So that's the trick to do here, because if you take the path y equals x, the point is that every instance, like every time you see y, you can just replace that with x. So let me put x times x divided by x squared plus y squared, but now y squared becomes x squared. Is that making sense? So the idea of like choosing a path is just that you turn like the limit that depends on two variables into a limit that depends on just like a single variable. So you turn it into like a calc1 limit, basically. And so since the only variable that remains is x, like the limit just becomes like the limit as x approaches 0. Okay. And so that gives you the limit as x approaches 0 of x squared divided by 2x squared. So the x squareds cancel, so you just get 1. Okay, so what that means is that if you're walking like along this line, the value for the limit that you get is just 1/2. Okay. Yeah.
So, the implication for x, y, or x plus y squared is that it's in 3 space.
So the graph itself, right? If you were to plot the graph is actually in 3D space, right?
Or is it like, is that itself like can't graph then, right? It would have to be set equal to something.
Oh, well, so the thing, like, you can think, I mean, if you actually, like, there are two ways to think about it. Like, if you have something like xy over x squared plus y squared, this would be my preferred way to think about it. So think about this as let me call it T for temperature. So think about this like kind of like as the temperature at the point x comma y, right? So you have like a thermometer or whatever, and at every point on the plane you can measure the temperature, and you just imagine that it's given by this expression, right? So the limit is asking, what do you get as you are approaching the origin, right? Like, so you have like a thermometer with you, you're moving towards the origin, and then you're asking what's the value that the thermometer is that you're reading on it, if that makes sense. So what I'm saying here is that as you walk towards the origin along this line, the value that you would get is 1/2, right? Does that make sense? So for the limit, like the point is that for the limit to exist, kind of like no matter how you got to the origin, everyone has to give the same reading for the temperature. Otherwise, there's no overall limit, in the same way in which before, if the one-sided limits were different, there's no overall limit. So that's kind of like the analog. You could think about it also like as kind of like the graphs living in 3 dimensions, but it's easier just kind of like to stick to the plane. And it's just, oh, you have like this temperature at a given point, and now we're asking how does that behave? Is that making sense?
Yeah.
Now, okay, so oh, sorry, and I should have said that obvious, like, why is it that I don't plug in just x and y equal to 0, 0, right? Like, maybe that's like the first thing you would have tried to do. But the point is, like, if you just try to do like a naive plug-in, you just get 0 times 0, which is 0 divided by 0, right? So you get 0 over 0, and that's exactly the whole point of limits, right? That when you get 0 over 0, it's not, you have to think a little bit harder, like, on what's going to happen. So I'm giving you something interesting where like you cannot just plug in, because if you could just plug in, then there's no this point in having this conversation. So okay, so now I'm saying that that is the reading, like again, that would be the reading of the temperature that you get if you move along this line. Now there are other ways to reach the origin. So I don't know if anyone wants to suggest yeah.
Y equals x squared.
You could, okay, let's try to see what happens with, good, let's try to check with y equals x squared. And then actually, I think this one is going to work. It's a little bit of an overkill because actually you could just have used lights, but it's good to try to see what happens with the parabola. So good. Let's try to. So what happens now? So now I'm going to use the parabola right? So now I'm using the parabola. Y equals x squared. So what happens here? Like, again, the idea is every time you see y, replace it with x squared. So you get x times y, but that's now x times x squared divided by x squared plus y squared, but y squared becomes x to the 4, right? So that's what you get here. So that's the limit as x approaches 0. So let before like doing some simplification, let me just put x cubed here divided by x squared plus x to the 4. So the easiest thing you can do is like factorize an x squared downstairs. So when you do that, right, so you can cancel, like, you can simplify the numerator a little bit, so you get x over 1 plus x squared. So far, so good. Is that making sense? And now this is a good version of the limit because now I can just plug in, right? Like the numerator, like now the denominator is no longer problematic. So it's just like 0 over 1, right? When you evaluate the limit, you get 0 over 1, and that's just 0, right? So that way, that means that as you're, what this is saying is that as you are approaching this, the origin, the value of the temperature that you're getting goes towards 0 as you move closer and closer to the origin, if you move along the parabola. Is that okay? Is that making sense? And that's it. It's right, because like now you found that if you move along the line, right? So if you move along the line, you get the value 1/2 in the limit. If you move along the parabola, you get the value 0, right? So this is the analog of like, the two one-sided limits being different. And so what you would like to say is that there's no overall limit because you found two routes that have different values. So what you want to say is that this limit does not exist. Since the answer depends, since the limit depends on the path that reaches 0, the origin, since the limit on the path that reaches the origin. That making sense so far, so good. Questions about this?
I guess, like, physically, what does like a discontinuous, like, function like this look like?
I mean, okay, this one, it is doing something crazy near the origin, right? Because you're getting all these different values. So it's kind of like, actually, I don't know. Let me try to see if I can plot it because it's harder. For example, in the one variable case, it's just literally that it looks like it has like a jump, right? But here it can do like more crazy stuff. Let's see if I can show you how this looks like. Here. Because the thing is, like, since this doesn't behave that nicely, I'm not sure if the GeoGebra will be able to plot something that looks kind of realistic enough. But let's see. Let me try it first.
Basically, like, when a function like means it can't like make a 3D surface.
I mean, if okay, so let's see. Let's let the animate. It is easier to just show the animation like happens with the animation. It is a surface, like, the graph is kind of like a surface, like away from the function. So okay, so you have to like going back to these domain questions. So, like this function, like the only issue that it has in terms of the formula is potentially at the origin, right? Because the only problem this function has is when the denominator becomes 0 in terms of trying to evaluate it. So the domain of the function is kind of like the entire plane minus the origin, if you want to think about it in terms of domain. So the function is actually okay in terms of behavior, except potentially at the origin. So now you look at this and, okay, it doesn't look too bad, but you have to start zooming in because like that's where the issue starts to arise. So, you know, as you start zooming in, like, I don't know if it looks like that is like, I don't know if you can tell like that there's more like kind of like weird stuff happening here because the function doesn't know what value to take at the origin. So it's trying to take a bunch of different values. So like there are like directions, like there are directions where you're trying to get 0, and there are other directions where you're trying to get 1/2. There will be other directions where you're trying to get 3, maybe. So there are a bunch of different values that the function wants to take there. And you know, as you kind of, and so you see like kind of like the surface is breaking in a sense, like it, of course, it's kind of hard to like really show that on the computer because you know, it's very behaving very erratically there. But yeah, you should think about it kind of like the function is trying to take bunch of different values at that point, so like it doesn't know where to go, basically, if that makes sense. So but yeah, you can kind of see it trying to be twisted and all do all sorts of crazy things. Um, um, Is that making sense so far, sir? Okay, so here's an actual useful trick in many of these problems, like when you're asked to find whether a limit exists or not. So, you know, here, like, for example, one of the paths I took was y equals x. I also took the parabola. You may want to try something which is a little bit more systematic. So a good thing to try, like here's like a good option. By the way, all the limits that, again, limits are not as important in this course like in Calc 1. Like in Calc 1, you spend tons of like weeks or sections talking about limits. Today is like the only day we'll talk about limits. So I'm just giving you like the basics so that you have like a feeling for how the limits behave in like when there are more variables involved. So so it's not that we're going to like, you know, because we're not interested in every possible detail, all our limits will just be at the origin because that's enough to kind of like show what's going on like qualitatively. So since we only care about limits at the origin, and you know, there's a very easy class of paths that you can take that approach the origin, which is just like a straight line passing through the origin, right? So what's the equation of a straight line passing through the origin? It's just y equals mx, right? There's no b because like it's going through the origin, right? So instead of being mx plus b, it's just mx plus 0. So a good thing to try with this type of problems is just take y equals mx to see what happens. So let's take y equals mx. So here, since it goes like so, because this is a line through the origin, right? So what happens here? So if you do that, what's the answer with this limit? So replace y with mx, so you get what m x squared divided by x squared plus m squared x squared, right? That's what happens when you change y with mx. So now both the numerator and the denominator each has like a factor of x squared, so you can get rid of the x squares. And this no longer depends on x, so there's really no limit to evaluate. So you can just say that that's the answer. Right? And so what can you conclude here? That the answer for the limit that you get actually depends on the slope of the line, right? So m is the slope of the line. So for different values of slope, the number that you're getting would be different, right? So this depends on the slope. So for example, when the slope was 1, which was the case y equals x, right? we get 1/1 + 1, which is 1/2, right? So this recovers the previous calculation at the beginning. But if someone had wanted to take the line y = 2x, right? Now you know automatically what the answer would have been, because it's 2/1 + 4, which is 2/5. So all that I'm trying to say is that, like, writing it in this format allows you to try infinitely many lines at once. That's a cool thing about this method. So, and the idea is that if the answer depends on m, there's no way for this limit to exist, because then you just start playing with different values of the slope and then you get different answers. So the idea, let me write it down here. So this is like a very useful strategy that when the limit does not exist, like, happens to work more or less all the time for the problems we're working with. But like, so when analyzing if you try y = mx, and the limit that you get depends on m, then the limit cannot exist. Okay, that makes sense. Yeah.
Is there a way to prove that the limit does exist? Because it seems like you need to do a counter example to show that doesn't exist, but is there a way to prove it for that exists for like all?
Yes, that's my next example, actually.
Oh.
Yeah. So for like kind of like this limit problems break into two categories. One is it does not exist, right? If you want to show that something does not exist, this is like the general strategy, try different paths, and just check that they give you different answers. What I'm saying here is that a good place to start with is just like the lines. So if the lines already give you different values, then you're done, nothing else to worry about. But now let's check something that actually will exist, and this one is a little bit more tricky. So in the two types of problems, yeah, this second type is can be a bit more confusing. So that's why I want to spend some more extra time discussing it. So can I raise here like questions? Okay, so I'm going to do a very small change to this expression, and you'll see that's enough to make the limit exist. So instead of having xy in the numerator, I'm just going to put x squared times y. So the only thing I'm going to change is like the coefficient of x on the top. So let me put x squared y divided by x squared plus y. Okay. And then I'll show you how the graph looks like, because it's also fun to compare that with the previous one. So what happens here? Like, again, like, maybe you have no idea whatsoever on how this limit is going to behave, right? And so you're like kind of like testing things out. And then you say, well, let's try with this line stuff, because like we just discussed that maybe the lines help you understand whether there's a limit or not. So what happened? What is the behavior of this limit along lines? So let's try first the line y = mx. So you get x squared times mx, right? Divided by x squared plus y squared, and y squared becomes m squared x squared, right? So, this becomes, limit, sorry, and now it does no longer, there's no more y, so let me just put x approaches 0. So you get this thing. You get mx cubed, divided by x squared. I'm factorizing an x squared here, so I'll put 1 plus m squared. Okay. So now I can cancel the x squares, right? But now there's a survivor in the numerator because I increase the degree of x, right? So like again, the limit as x approaches 0 of mx divided by 1 plus m squared. Oh, so I made a, no, this is fine, right? Because this is like quadratic. Okay, so. And what is its limit? I mean, it's just 0, right? Because of now the x in the numerator makes it go to 0. Okay. So now what's happening is that if you go to the origin through any line, right? All the lines agree that the limit should be 0. So far so good. That making sense. So okay, so this is good indication that something interesting is going on. The thing is like, in principle, theoretically, that's not enough to say that the limit is 0 because the way lines are not the only way to approach the origin, right? So for just to do another example, like you could also approach the origin using like a parabola, like the one that we tried last time as well. So what happens if you try like the parabola y equals x squared? You would get now the limit as x approaches 0, So this is still x squared, y becomes x squared also. And so you get now x squared plus x to the 4, right? And again, I can cancel an x squared on the top and bottom. So like I get limit as x approaches 0 of x squared divided by 1 plus x squared, right? And that continues to be 0, right? So in this case, it's still true that, if we had found, for example, along this parabola, that the limit is 1/2, then we're done, right? Like the limit would not have existed. But we also notice here that the limit happens to be 0, even if you use a parabola. So what but again, not it could be a bit repetitive, but just the fact that it agrees, it gives you 0 for lines and it gives you 0 for this parabola. That doesn't mean that it would always give you 0 because like you could have tried like y equals x cubed. You could have tried tons of other things that also approach the origin. So obviously, so the idea is you don't want to try every single function, every single path that goes to the origin. Like that is literally infinitely many options to check for. So the strategy to try to prove what this does tell you that the limit looks like maybe it wants to be 0, right? But so like the strategy is not to go through every possible path. That would take like an eternity. So this is actually where we switch methods and go to what's the squeeze theorem or sandwich theorem, if you remember that from Calc 1. So just to explain, so like this, let me just say what's going on as of now. So this suggests that the limit should be 0, right? But to prove it, we do need the squeeze theorem. So like this is like an important thing. If there's a limit that you want to show that exists, you must use a squeeze theorem. Like that's the only way. Again, we're not spending too much time on limits. So the only way to show that a limit exists here is via the squeeze theorem that I'm about to remind you. But to prove it exists, you must use so that's also called the sandwich theorem sometimes, right? So what's the idea here? Before explaining it, I just need to remind you quickly about how polar coordinates work, which I think I have said a couple of things before. But just as a quick reminder, if you have x, y, right, if you have a point x comma y, what's polar coordinates? Polar coordinates is that you have the variable r, right, which is the distance to the origin, and you have this angle theta. So in polar coordinates, x is r cosine of theta, and y is r sine of theta. Right, so the point, instead of being given in terms of x and y, you could also specify the point on the plane in terms of r and theta. And the most important thing here, which again is just like the Pythagoras theorem, is that r squared equals x squared plus y squared. So the most important identity that we're going to use for this type of problems is that r squared is x squared. Okay, so sounds good. We'll use polar a lot during the course, so like this is kind of like the first part where they really become important. So why? So the strategy is that to prove that the limit exists, what ends up being easier is to prove that the limit exists when after switching to polar coordinates. So if you want to switch the limit to polar, let's switch. So what does that mean here? So x squared is just r squared cosine square of theta, right? You square the x. Let me use different colors. So x squared is r squared cosine square of theta, and y is r sine of theta, right? So that's what the numerator gives you. And then x squared plus y squared is the identity that, oops, I forgot the limit. Okay, so let me just write this a little bit smaller. I'm about to say something about this in a moment. And so, and then x squared plus y squared is r squared. Okay, so that is like the same expression, just rewritten in polar, which is fine. The thing that you have to ask, think of a little bit more about is what should you put here, right? So before, when it was in terms of the variables x and y, you would say that x, y approach the origin, right? If you think of, so what that means is that the point that you're taking is going towards the origin, right? Like that's how the point is moving. So if the point is moving towards the origin, right? What happens with the distance to the origin? That also needs to be going towards zero. That's the only way to reach the origin. So essentially, what I'm trying to say, and you can also see it here from here, because if x and y are becoming really, really small, they're going towards zero, then r also has to be going towards zero. So my point is that when you switch to polar, what you can always say is that r has to be going towards zero. Is that making sense? So that's the important thing. But what is theta? Theta is the angle, right? So theta is an angle, but the problem is that you cannot really say anything about how the angle is behaving. For example, if you move this way, it looks like the angle is pi over 4. If you move this way, the angle would be 0. You could also be like kind of spiraling down towards the origin. So the theta could be changing constantly in values as you approach the origin. So what I'm trying to say is that there's nothing that you can, like theta does not necessarily approach a specific value, if that makes sense. So the theta is actually free to do whatever it wants. And like, doesn't need to approach, doesn't need to approach anything. A specific value. Is that making sense?
Converting,
Mhm.
expression to polar.
Mhm.
I was just wondering why like r is squared and cosine is squared on the top. Because like if x is equal to r cosine.
Oh, okay, yes, I'm sorry, like, okay, so implicitly, I miscopied this one, it was an, yeah, no. I think I may have you, like, when I copied it again, I forgot, I'm looking at the one that had the square on the top for X, so yeah. No, thanks, good, any other questions? Okay, so what I'm trying to say is that in polar, R always goes to 0, that's something you can assume, but theta, we don't know what it's doing, so it can be doing some like crazy behavior. So, well, let's just like simplify this a little bit. There's an R square here and then an R square here that can be canceled, so you just actually end up getting R cosine square of theta times sine of theta. Okay, so the idea is that for this limit to exist, the the limit must be the same for any possible value of theta. That's the idea. So in polar, so for this limit to exist, it must give you the same answer regardless of the value of theta. It must give answer regardless of what theta is. Okay, and how do you show that the answer does not depend on theta? This is where you will use a squeeze theorem. Okay, so if you I mean, I probably haven't done squeeze theorem stuff in a long time, but the idea. What was like the typical squeeze theorem problem in COP 1? Just to remind you. The typical squeeze theorem problem was something like x approaches 0 of x times sine of 1 over x. I don't know if you remember that those types of limits. The idea is that you cannot just evaluate at 0 there, but what you would use is the fact that sine is always between -1 and 1. Okay, so it is something similar to what we're doing to do here. So what we're going to use, and this is again like the most important part, like for the squeezing, we'll use that cosine of theta is between -1 and 1, and the sine of theta is between -1 and 1, regardless of the value of theta, right? Like cosine and sine are always between 1 and -1, for regardless of what theta is. Okay, and so why is that useful? Because let's think about r cosine squared times sine of theta. The idea of calling this a squeeze theorem is that you want to squeeze this between two things that you understand more easily. Okay, so what you have to ask is like how big, right? Here's like how you could think about it. What's the largest, what's the what's the most as a number that cosine squared sine could become, right? All these are always numbers between -1 and 1, right? So the biggest that this product could be is 1, if that makes sense. Because like when you multiply numbers between -1 and 1, you always keep getting numbers between -1 and 1. You cannot grow out of it, So the most that this can be, so the large, and it may not even get there, right? It may not be 1 at any value. Actually, it cannot it cannot be one at any specific value. But regardless, like the largest this could be one. So that means that this is always less than R times one. Okay. And what's the smallest that this quantity could be? Again, like cosine squared, I mean, it's like between 0 and 1, actually. That doesn't matter too much. And like the sign can be between -1 and 1. So again, when you multiply them, it's kind of like the same, but on the other side, like the most negative this can become is -1. And again, it's not even true that it would reach -1. I'm just saying, like, for sure, you cannot get like -2 or -3 with like something like that. So the smallest it could be. Is that making sense? So that means that this is between, and so R is just R, so let's just keep it here, but the most negative this can become potentially is -1. Okay? So what we end up finding is that this quantity that we're interested in taking the limit of is between these two things, right? And so when you take the limit on every side of the inequality, that's like how the Swiss theorem would work, right? The thing is that now, you can say very easily what's happened with the, like, the ends of the inequality. Because as R approaches 0, this thing just goes to R, right? Sorry, this thing just goes to 0. And as R approaches 0, this thing goes to 0. So it forces the thing in the middle to go to 0 as well. So this goes to 0 by the Swiss theorem. So that's how you end up saying that the limit is 0.
Wait, is it possible to do the same method if, X and Y didn't approach it, like, let's say they approach like 1, 1.
Oh, so you can, the thing is like then you have to translate, when you do it's kind of like a translation of polar coordinates.
Oh.
Which can be done, but it's a little bit tedious, because like the algebra becomes a bit more messy. So like that's why we're just focusing on the origin because that's just more straightforward. But yeah, like you could like essentially you kind of shift the polar coordinates so that they're centered at 1, 1. So which is essentially a saying like every limit is a limit to the origin in cup 1 even, by making a change of variable. So for example, if you had like if you had something like limit of x approaches 1, right, of x minus 1 over like x plus 1, whatever, you could make like a change of variables like t equals x minus 1, which is not something like you do that much in cup 1, but and so as x approaches 1, right, what happens? T approaches 0, right? So it's the same as saying the limit as t approaches 0 of like what's x minus 1, t, and x plus 1 becomes x plus 1 becomes t plus 1, right?
T plus 2.
T plus 2, yeah, thanks. Good, thanks. So you see, like, secretly every cup one limit is also a limit to zero. Obviously, you don't think about it that way, but like, just by shifting, like, the coordinates, you can always do that. So just for like, again, the thing is like the limits don't play such a big role in this course. So that's why we're like, and even in cup one, like the point of limits is that you kind of forget about them. That's how like calculus works well, because then you just get to the rules of derivatives and the rules of integrals, and then you're done. Like, you don't have to think about things like in terms of the limits. And that's what makes it efficient to work with. So it's kind of like the same principle here. Like everything is secretly going to be defined in terms of a limit, but we're never going to compute things from the limit point of view. It's just that it's like what's important here to understand is that on the plane you have more room. More room means more directions. So saying that a limit exists is something like stronger now because it's saying, oh, it exists regardless of all these infinite many paths who have chosen, which is like way more powerful than just saying it exists because you approach it from the left or the right, like, positive or negative values. So it's kind of like a stronger condition. It is stronger to have like the limit exists in count three because there are more paths that you could have taken. Like, so that's kind of like the important thing here. But if we don't want to kind of go into all the subtleties because it's just like to get like a sense of like, how that works. If that makes sense. Does that answer your question? Let me show you actually how the graph looks, and then I'll do another example of limits. Because this is like again, this is the last topic. Oh, okay, turn it on, which is what I needed. So that's good. No, I forgot where. Oh, yes, mine. Okay, so. Again, so this was like the function from before, that doesn't have a limit at the origin. And now I'm going to fix that folks by just squaring the x. And if you look at it, like it does behave a lot like, it is not having like these crazy oscillations like near the origin. It in fact kind of starts becoming flatter and flatter. Like it gets flattened up as you approach the origin. And so the limit and some existing because of that. Okay, so like multiplying by x kind of controls like the behavior, like the fluctuations of the function, like of the original function. So now that's why this one exists. Okay, let me do another, like one more example, and also write something about limits. So what I have been saying is that for this type of problems, there, you know, so there are only two types of limit problems. So the type one is where you want to show it does not exist. So it does not exist. And for that, what you have to do is find two paths where the compute the limit along two different paths that give you different numbers. So compute limit along two paths that give different values. And the other one, and for example, here's where you can use and try y equals mx. And try y equals mx to see if the answer depends on that. So that's one thing that you could do. And then for the type two problems, it's like the one that we just did. Or you want to show that it does exist, right? I want to show And then you switch to polar. That's the only way we have to show that a limit exists. So switch to polar. And show that the limit does not depend on theta. So basically. So let me, like, if I do, let me do one more of each. And I'll do this one in two different ways also to show you that like there are a couple of alternatives. So. What makes this confused, like what makes this confusing sometimes, like is that you're not told ahead of time whether the limit should exist or not. So part of the problem is to decide whether you want to try to show it exists or not. So you do have to get some acquaintance with these limit problems to kind of develop like an intuition for whether or not it should exist. A good hint is that most of the time for this type of problems, you'll see something like x squared plus y squared. So you'll like the combination tends like, typically the expression will involve, typically these will have x squared plus y squared somewhere in the formula. That's like a good hint for things to try. Okay. So let me do some examples. So let's say you take this limit, which is x plus y divided like by x minus y, right? So you want to show, like you want to see whether it exists or not. So if you're not like sure, you can just try the first approach. So just try to, yeah.
I was gonna ask for type two.
Mhm.
So if the limit, does depend on, I guess, what I was asking is, could you also conclusively show, that the limit doesn't exist with that method?
Yeah, that's actually what I'm going to do here. Yeah, like I'm going to do this in two different ways, but actually using the polar switch to show that it also works to show the limit does not exist. So for example, if you have like a limit like that, what happens if you try something like y equals mx, right? To like just like I should have used like the other columns. So you get the limit as x approaches 0, x plus y, so this is x plus mx divided by x minus y, so x minus mx. So you see x cancels here, so you get the limit as x approaches 0 of 1 plus m over 1 minus m. And that's 1 plus m over 1 minus m because there's no longer any x's. So then this clearly depends on the slope, right? So this depends on m. So this one cannot exist, right? So can't exist. Does that make sense? Now here's a different way to do it, which is with polar coordinates. So polar also works in this case. So let me do the same limit with polar. So if you use polar, which is x equals r cosine of theta, and y equals r sine of theta, right? What do you get here? So x becomes r cosine of theta, y becomes r sine of theta, and then x becomes r cosine of theta, and y becomes r sine of theta, And again, what I was saying is that when you switch to polar, the only thing you can say for sure is that R is going to zero, but you cannot say anything about theta. So what happens here is like, again, everything has like a factor of R, so you can get rid of that. Right? So there's no more R, so the limit just gives you that. But what's the issue here? The issue is like theta could be anything. Theta, like if you think about it as an angle, can be any number, angle between 0 and 2 pi. So these will depend on the values, the particular values that you give to theta. So this like limit, right, depends on theta. So it can't exist. Does that make sense? So, yeah.
So for like, from the exam, will we only be doing limits that approach the origin?
Yes. Yeah, so, and for, type 1, actually, yeah, like you can also try to do it in polar, which is what I'm, the only thing is that, so the idea is like, if you switch to polar, then that's fine, but then you just have to make sure that it does depend on theta, the answer to say that the limit does not exist, but they're always like, yeah, approaching the origin. Is that okay? Another one? Okay, so let me do an example of the another example of the squeeze theorem. So here's one. Here's another example. Whoops. Okay, let's say you had something like that. It does involve like x squared plus y squared, there's an x squared plus y squared somewhere in the expression. So, you could either try first to do this y equals mx stuff, or you can just trust the hint that I wrote earlier. And if you see something like x squared plus y squared, it is convenient to switch already to polar just because that becomes very nice in polar. So if you switch to polar, you get the limit as r approaches 0 of x. X is now r cosine of theta. And now the other one becomes 3r sine of theta, right? And then the stuff inside the square root becomes r root of r squared, right? So you get the limit as r approaches 0. Okay, let's see. Let me put let's put yeah, like a quartic root, otherwise it won't work. Okay. So it's just I just want like an r to the 1/2 here. R cosine theta. Sine theta, or root of r, or r to the 1/2. So that's really if you can write it this way. You can like so there's like an r with this r to the 1/2. You get an r to the 1/2 on the top. So you get a cosine of theta plus 3 sine of theta. Is that making sense? Okay. And here, like, this is like a good comparison between what happened here and what happened there. So here, like, you have an expression that involves theta, but there's something with r that is trying to go to 0. Okay. In fact, I can write this as root of r to make it more clear. So let me write it like root of r. Whereas here, like all the dependency on root of r went on r went away. So there's nothing really to control the trigonometric like the theta stuff in this limit because the r is canceled. But here there's something like that depends on r. that it can sort of like save the day and put this under control. So that's where the squeeze argument comes in, because and I'm almost done. I'll just finish doing the squeeze thing here. So here, like, the idea is to squeeze this between numbers, certain fixed values, like that, the trick stuff, you want to control it with certain fixed values. So again, like, you don't have to overthink this too much, just like do something like a simple inequality. So you say, well, what's the biggest that cosine could be? It could be 1, right? What's the biggest that 3 sine could be? Could be 3, right? That's the largest. So the sum, the most it could be is 4, okay? That's it. Like, it probably will be most of the time less than 4. It actually would never get 4. You're not trying to give like what people call like a sharp bound. Like, you're just trying to give something that works, you know. So 4 works, and that's enough. You know, you're not trying to find like the most precise bound that works. So you can just put 4 here. Is that making sense? Similarly with this one, like, then you have to ask, what's the most negative this could become? The most negative this could become is -1, and the most negative this could become is -3, so you would get -4. Maybe it is always like between -2 and 2, you know, or something like that, but we don't care. We just need some finite numbers, and that's it. Like, the only thing we don't want is for this to kind of like be between -infinity and infinity, because then you cannot say anything. Yeah.
Say that for that limit,
Mhm.
there's not like a left side, right? Like, it can't really exist.
Oh, so.
R was approaching the negative side. Is that
Oh,
like-
that's a good point. So the thing is, like, R in polar, the way the convention we set it up is always non-negative. Because it's always like the distance to the origin, so we always like, so yeah, here all the R's going to 0 are really like R pluses. Because that's the only thing that exists in terms of R. Yeah, good. But so what I'm trying to say is like, you know, whenever you think about what inequalities to put here, just like kind of like do like the crunch it like in your head, but without like overthinking it. So you know that between 4 and -4 works. You don't have to think whether you needed something smaller. Once you find something easy, then you're done. Because this is like -4 times root of R, you know, as this approaches 0. Okay, let me see. That's almost done. So like, when as this goes to 0, this just gives you 0 here, this gives you 0 here. And then by the squeeze theorem, this would go to 0. That making sense? So that is how you would show that this limit exists. So again, there are only 2 types of problems with limits. And after you do a couple of them, you kind of get like an intuition for when one happens and the other does not. But if anything, you can always kind of like check by switching to polar and see how things are behaving. So just to finish, I'll send before we leave, just in case. So there was like, I decided not to cover this topic because it just takes too much time, but there's this topic called vector projections. So I'll send an announcement about it just to remind you, but like, I won't include that on the exam. So officially, like, all the material is here. So like, just to at least tell you quickly what the vector projection is, like with GeoGebra. The idea is like, if you have 2 vectors, you know, you can kind of like draw the shadow that one vector makes along the other one, kind of like if you had like a light bulb. So that is, so the shadow would be kind of like this red vector that you see here. So like the vector projection is just like, what's the shadow that one vector makes along another vector? And then there's like a formula, like, let me change one of the vectors so that you see like what I mean by shadow. So there's like a formula for how to compute this shadow vector using the dot product. So you can, like, it's on the study guide if you want to see it. It's not too difficult, but there's not really anything else that we use it for, like in the course. So like, I won't include it on the exam. But just to let you know, I think one of the GeoGebra assignments is just to take some screenshots of this animation. So yeah, that you should still take the pictures, but it's just I just give you like two vectors, you put them here and then you take the picture of what you get. So if you take linear algebra, that's something that's useful. You use it a lot of the time, but not in this class. So so officially we just finished the topics for the exam. So as I said, like I'll give you extra office hours next week, and also the TA Karuna will also give you extra office hours next week as well. So I'll see you on Monday. We'll start out a new session.